Okay. Okay. Thank you for this opportunity to be here and talk to you about my recent work. So today I will present you a new description of movement of particles, massive and also photons, in the Schwarzschild spacetime. And this presentation is based on my recent work, which is now available on arXiv, but it is already accepted to publication by classical quantum gravity. Okay, so let's begin. I have to use. Okay, so this problem of solving equation of motion in Schwarzschild metric is as old as special relativity, because the first person who obtained Schwarzschild metric was Schwarzschild himself. And in his work, Schwarzschild do just that. He wasn't interested in solving equation of motion. He just solved equations of Einstein, and that's it. And the first person who solved equations of motion was Drost. And he also obtained Schwarzschild metric independently from Schwarzschild, because at that time Schwarzschild was on war and Drost was in Netherlands, I think, and then they don't know about themselves. And in his work, in Drost's work, Drost obtained some solutions. He described a few important for him trajectories in a very fixed way using Weierstrass elliptic functions, and he was the first person to do this in this way. And after him, Hagihara, based on Drost's work, gave as a first person a full description of every physical type of trajectories in Schwarzschild metric. After 30 years, Darwin and later Plebański and Miernik worked on the same topic, and they gave also description very similar to Hagihara, because they categorized in the same way different types of trajectories, but they used Legend elliptic integrals to their explicit solutions. And here, interesting thing is that you can find in Darwin work and Plebański-Miernik that the sentence that they are aware that their results or their calculations supposed to be done 30 years earlier, but they don't know why that wasn't done, and that's why they start to calculating this. They were right, because Hagihara and Drost done it, but they wasn't aware of these publications. At that time, knowledge was very transfer of knowledge was very separate, so it was hard to get this publication or even those. Okay, and in later years, there was not significant development in this area. We modernized the way in which we categorize trajectories. We start using effective potential to do this, and it simplifies a lot our descriptions. And a very good example of the paper in this new way, but based on this previous work, is a paper of Kostic from 2014, and his work is based in some way on Plebański results, but he wasn't aware of Plebański work. and it's done in modernized way of describing trajectories. And the first person who tries to something new, and when I say something new, I mean that tries a new method to solve equation of motion was Schwarzschild, and in 2011 he used in his work simplified Biermann-Weierstrass formula. I will show you later how it looks, and he used this because he wants to find very simple post-Newtonian corrections from the Schwarzschild model. And because he was, I think, I'm not sure because I never met him, but because he was only interested in this post-Newtonian corrections, he stops there and don't go quite into his idea and try to he wants to get something more from this formula. And this work is our starting point. We decide to use a full formula and full theorem of Weierstrass-Biermann and see what we will get from it. Okay. So typically we have to start with metric. Here is a Schwarzschild stochasymmetric metric. RS is Schwarzschild radius. And in this work, we change our coordinates to what you can understand as a general Eddington-Finkelstein coordinates, because we don't want to have irregularities on the horizon. There are a couple of reasons why it is important for us. But here, it doesn't matter. You can compute everything, what I will show you, once again for the typical Schwarzschild, and you will have similar results, and calculation will be much simpler even. So, but this is how we do it in our work. Okay.
This eta of theta.
Yes, this is a foliation of time foliation because we want to. Excuse, I'm sorry. This new parameter is okay. So why I said that this is.
I think that in this formula one, maybe there is a typo there. There is eta at dr squared. Dr squared coefficient at dr squared and eta. Doesn't make sense.
Dr squared?
Yeah, one line below.
Here?
Yeah, dr squared.
Dr squared, yeah.
The coefficient.
Yeah.
And
Yes.
eta in front of this.
Yes, it's not a mistake.
So I think that eta is defined as a function of r. R has units, which are meters. And now you apply r to 2. And 2 doesn't have units. So
when we r to 2, this goes to 1 and ends and yeah.
okay, but is it if eta is 0, then this is just
Finkelstein. Yeah, eta is 1. We have simple Eddington-Finkelstein coordinates. This is why I said this is our general way.
Okay.
And eta is like you choose the correlation of time. You can always you can choose different correlation of time, and this is the general way of describing this.
I'm so wondering. So there is a function which you can apply to variable that has units and also to variable that doesn't have units. I didn't know such functions.
It's not eta applies to 2 minus and eta, but eta times.
Yes, it's at times.
Oh, it's
times.
Okay, good. I take it back.
Okay, okay, so I'll say it also. Okay, so yeah, it's because it's like here. Okay, so I can go to the next slide. Yes.
Yeah.
Mhm. Okay. So with a given metric, there are a few ways to obtain equation of motion. You can use geodesic equation, Lagrangian, and of course Hamilton formulas. And we decide to use Hamiltonian. Here is a Hamiltonian for particle moving along the geodesics, and we write down Hamilton's equations, and from them you can easily obtain, of course, geodesics equation. This is a standard way of dealing with this topic. And what's quite important here, this parameter is Schwarzschild proper time. So we take proper time and divide it by mass of the West mass particle. And this is done because thanks to this, our Hamiltonian looks very nice. It's here, we got this, and our equations are much better for us, I might say. Okay, but with using metric and Hamiltonian description, we can quickly obtain, okay, how in this particular example Hamiltonian looks like. And with a given Hamiltonian, we can quickly read from it conserved quantities. We have conserved energy, conserved azimuthal angular momentum, and we can check that, okay, there is also one more conserved quantity, total angular momentum. Okay, with this knowledge, we can now try to write down a equation of motion from Hamilton's equations, and this is how they looks. Here, capital U is effective potential, and these equations are for massive particle, but it can be done also for photons, and with the difference in effective potential, it will be simpler, basically. And there is one thing here, quite important, is epsilons R and epsilons theta. They stands for they correspond to direction in which you choose to move. If, for example, you choose to move inwards of coordinate system, then you choose epsilon R equals -1. If you choose to move outside of coordinate system, then it's +1. And the same is with theta. All right. Now we have one more step, basically scaling, because we don't want to work with m's and we'll have dimensionless variables. So this is how we obtain this dimensionless equation of motions. And the most important thing here is to remember that C stands for radial distance, and this epsilon, stands for conserved energy, and lambdas for angular momentum. Okay. Same. Now, because we work in spherical symmetry, we can use this property of our space-time, and for every trajectory, you can notice that, okay, if we have some trajectory in this space-time, then we can always choose a plane in which particles moves. And when we have this, when we choose this plane, we can describe this by basis vectors, which are given here. And okay, this description is not static. It's not very pleasant to see. But let me show you geometrical interpretation of that. So basically, we have some local Cartesian coordinate system and some particle moves right here, and you can always choose this basis in which the movement of these particles appears. And for description movement like this, the most important thing for us is this psi angle. It stands for true anomaly. Yes, and yeah. How to look? Why it's important? Because when we go through calculations and try to obtain from these construction some results useful for us, then we can notice, okay, there is some equality between the relation between conserved angular momentums and inclination. And thanks to this, we can obtain another relation between true anomaly and angles phi and theta.
Sorry, I don't understand. So
Yes.
what is true anomaly? Is it a constant or is
No, it's changing. It's yes. So it's basically this angle, and it moves with the particle.
this angle? When you say this angle, I don't know which angle.
Okay. Here it goes from here and here. This is a radial distance of particle, and it goes from E1, which is one of the base vectors which we calculate from our construction, and it's typical construction. This is a typical way from astronomy to calculate how particle moves, and this is astronomical. These angles are just astronomical way of.
Certainly, we can have one system of axes, yeah, laboratory axis. Then we rotate axis to such a position that we have plane.
Yes.
Motion, yeah.
Yes, and you can know this from celestial body mechanics. It's known there as the Euler, I think, rotations. You can always choose one system of axis and then choose different rotated in respect to this first one. And we just do this here and use astronomical notation because they do this all the time. It's all quick. It's like very old. And okay. And yes, after all of this, we can obtain these two relations. And this the system of this equation means that, okay, if we know angular momentums, conserved angular momentums, and the change of true anomaly, so this psi, then we can get the change of angle psi and theta. Because in this metric, all of the movement of particle happens in only one plane, always. This is not the same in kerr. For example, in kerr we have difference. We don't have stochastic, and then if we have more some velocity in the theta direction, then it will change. So this is only available here and maybe in the Reinstein-Nordstrom district. Okay. So what it does for us that now we can use only three equations without losing any generality in our description. So we have three equations to solve, And from our knowledge about conserved quantities, we can describe movements in the our starting Cartesian coordinate system.
So psi is this angle, psi, the first
Yes.
variable, what
It's a true anomaly. It's angle between
psi.
psi is a radial distance.
Radial distance. And tau is
Time, coordinate time, not the proper time, coordinate time. Yes. S is something, this Rescaled proper time. It's affine parameter. You can understand this as affine parameter.
I understand that you will use this function X of you still keep free function F.
Yes, but I will not use them. No, because the main goal here was to obtain the solution of the last one question also. And if you done this operation for normal Schwarzschild, you will obtain similar equations, but without this part. We want to calculate with this part because our different project, simulation of Wassow gas, we use this as a way of describing where the particle is. If you have simulation, we want to know how, when particle is in what place. Thanks to this, we can evaluate how many particles is in some place, and then after this, density of particles in a specific place. And but I'm showing you this because to prove you that it can be done in more complicated example and more general example. So in order to solve these equations, we have to, as the first step, connect these two equations, and just divide one by another, and as a result, we will obtain the square root of this polynomial. And our main goal here will be obtaining psi as a function of psi. So to do this, first let's simplify our description. This is a polynomial equation, so let's write this as a polynomial of the fourth degree. Here, A0, A1, A2, and A3 and 4 are constants. And this equation 10 after this solution looks like this. So last thing at that point we can do is to integrate this, and we will obtain this integral. And this is the point where we have to use this Weierstrass Biermann theorem. Up to this point, everything was quite classical. Everyone does it the same way. But here is the thing, the place when we start to do something different. But before this, let me ground your attention on one thing. Look, if f function will be negative function in some way, then after the square root, we'll obtain complex value, some complex value. So our equation here will not be a physical description of motion. We want real values. So our basic condition for every type of trajectory is that, this f function have to be 0 or positive, not negative. There's only one assumption to obtain real movement. Okay. Before Weierstrass go on, I have to say something about elliptic functions, because nowadays it's not taught, and myself I have to learn this, and I'm aware that okay, it's not common knowledge. So elliptic functions is a function on the complex plane which have one special feature, is Dolby periodicity. And this is a characteristic feature for only complex functions. We cannot have a real function which will satisfy this condition. So if we have a complex function which satisfies this condition, okay, with assuming additionally that it's analytical, then this function will be elliptic function. And there are many types, okay, not so many, few general types of elliptic functions. And the best one of them, the best defined, are Weierstrass elliptic functions. There's one of the depiction of how it looks. And it's so, this function is so good that there is even theorem saying that, okay, if you have any type of elliptic function, you can always depict this function by using Weierstrass P function or derivative of Weierstrass P function. So these functions are the basis of the theory of elliptic functions. And if we have a description in Weierstrass elliptic functions, we can be sure that okay, it's quite right. Yes. Okay. Now, theorem. So we start in this theorem with assumptions. We take some polynomial of 4th degree, and here we have G2 and G3 invariants. These invariants are part of theory of elliptic functions, and here we just have to postulate them in this way.
Invariant under what?
They are defined, as I remember from theory of this polynomial, that if you, I think, have a polynomial function like this, and you change variables of this function, for example, let's take c plus epsilon, then you obtain a different polynomial of 4th degree or so. However, if you count this invariant of this new polynomial, you will obtain the same number, I think, as I remember, because I read about them more than 1 year ago. And yeah, but I think it's that.
I think the invariance is the different so the result is
maybe. Maybe. I don't quite remember.
About the roots.
Okay. But yeah, and if you have why we need them, if you have normally elliptic function, this is okay, it depends on z, it's the main argument, but it's described also by G2 and G3 invariants. So, for example, if you try to code this function in Mathematica, use Weierstrass P, you have to give, okay, some argument angle, which you want to, and you have to give what invariants this function which you are interested have, what G2 and G3 is it's for this specific function. this is why we need this, but not exactly. Okay. Yeah. So after setting this, Weierstrass says, okay, let's take now integral in such a form. So let's compute z as a function of x, where x is the upper limit of our integral, and where the x0 is any constant you want to. And let's take this integral from 1 over the square root of this polynomial degree. Now, let's compare this to our results from the previous slides. This is our square root. It's the same. We have here a polynomial of the 4th degree, and the same integral boundaries. Okay. So what it will be? Weierstrass says that, okay, if you have this, then you can express x. So one of these boundaries, this x, as a function of z and your initial constant. What's more, you have also expression for p versus p functions and derivative versus p function used here in this formula. And here is how p or z is you can write it in different way. It depends on G2 and G3. Yeah. So
wait a moment. So we have a relation between x naught, which is starting point, x, which is finite point,
yes,
and z, which is
parameter in which you mark your way from x0 to x and x.
This is any point on between x naught and x.
No. It's like if you think about this geometrically. For our example, let's take our example. Here we have some rather distant x0 and another rather distant c, and then this is z from the Weierstrass-Riemann theorem. Here it will be our c, so it will be angle in which particle moves, particle marked, traveling from this first point to end point. And this is like now you treat this parameter as something in which you want to mark your way, something like proper time or affinity.
Okay, so we invert the relations. And instead of having z as a function of x and x naught, we write x as a function of x naught and z.
Yes, this is the main result of this theorem, and we want to use this because here this is our goal. It's here. We want to have a function of c as we want to have c as a function of c, and thanks to this theorem we can obtain this. Yeah, and now before next slides, let's look first on this p and p prime equations. As you can see, if f function is 0 or positive function here, then we can be sure that p Weierstrass p and the derivative of this Weierstrass p will be positive real number. Yeah. And that's why here, if we have this condition true, we can be sure this value will also be real. And in our problem, this is the basic condition for existing physical trajectory. So this formula describes in simplification, all types of trajectory, because it don't need any another conditions to distinguish between them. There's only this one condition that f have to be positive or equals to 0. And if it's it's true, then you can be sure that this function will always give us a real number. And yeah, here I write down this G2 and G3 invariants, and I keep by the Schwarzschild radius. By a reason, it will be helpful in next slide when I will talk about Post-Newtonian approximation. So yeah, it's basically here is equals to 1, but in the Post-Newtonian in the next slide it will be helpful to have this here. But before this, let's talk about more about this equation. So, as I said, this is true for every type of trajectory. It always will give us a real result, and what's more, it only depends on the initial conditions. You pick conserve energy, angular momentus, and initial position c0, and also this CR0. It's initial direction. For example, you can choose that, okay, at the starting point, C0 particle will go in the direction of black hole, so it will be negative 1, and you don't have to worry about anything. Especially, you don't have to worry about turning points. You just pick this condition, and this equation will give you all dynamics of particle. And this feature of this equation, that you don't have to worry about turning points, is especially important and new in this whole theory of solving Schwarzschild equations. And it will probably be very helpful in Kerr problem when we try to use this in the Kerr. Also, I can say that you can compute the same everything for Russian Nordstrom the same way, and you will don't have any major differences. It will also work perfectly there. Okay, so let's test this and see some approximations.
But you said that this sign it's selected at the initial position. So yes. After the turning point, it changes.
You don't have to worry about this.
Sorry, okay, but I'm worried.
Yeah, you are worried. Yes, you can prove that this equation will work after the turning point, and this sign, this p function will p prime, because it's not. I think it's odd function. Will work. Take care about this sign after the passing the turning point. Everything will be fine. Yes. Okay. And now let's talk about first test of this formula. Let's take a Post-Newtonian approximation. And the simplest way of doing this, and showing this on the one slide, is by examining the description with respect to turning points. You can always pick a turning point for the Schwarzschild, and it's defined here as a point in which our f function will be equal to 0. So if you have this, our formula looks like this, and this is the formula which Scharf used in his work on which we are based, or with which we start. And here, you have to control where are you with the turning points, because there is nothing to control you. And if you want to describe evolution, you have to, by yourself, pick where you want to go, because you start with from the pericenter or apocenter, and yeah, you have to be conscious what you want to describe. So this is the weakness of this description of the simplified formula. But here it will work very nice to show you significance of this equation. Okay, in this limit, Post-Newtonian limit, we can now look on about invariant G2 and G3. And this is why I saved this Schwarzschild radius, because when we taking this limit, we can, for the simplicity, forgot about variables with CS, and our G2 and G3 will just become 1/12 and 1/6 to the first yeah, this I forgot the word. I'm sorry. After okay, so if we have to the third power, if we have this and this expression for G2 and G3, then we can use it in expressing a P function, and this formula is general property of P function. You can check the proof of this in, I think, Bittman textbook, or you can just put it in the Mathematica, and it will give you as an output some function which is similar to this, because Mathematica use a different way of depicting trigonometric functions. So it will be something similar. Okay, now let's also introduce uncertainty, because and let's introduce this in the classical way. So let's define this as a ratio between two special points. First one is, I think, apocenter, and second one is pericenter. And with this, and after some quick calculations, you can obtain from this equation this formula, which this is a ellipse equation known from Kepler theory. So Andrzej says that if Kepler knew elliptic functions, he could come up with this formula, exception of this. They are very similar if you know how it works. Now, before just looking on the numerical results, let's say something about categorization of trajectories. And yeah, on this upper plots, there are plots of effective potential, and these plots are for two different values of angular momentum. You can see the changes of the shape of the potential and the types of trajectory which are available in such conditions. Here I draw how this trajectory would look like. These are the four basic types of trajectories, but our model also works in the special type, like, for example, trajectories which starts at the some point and comes inward to the coordinate system and start to roll around some radius, like the spiral trajectories. Okay, so now let's see how it works. Okay, the quality of this is not good, but on this picture I plot our results, which are the straight lines, and the numerical results, which are the dashed lines here and dot lines here. This area is the area of event horizon, and you can see that, okay, there are in good, there is no mistake here. Also for the second type, another type, and this scattered movements also. I think it's fine. Okay, so now I will show you how to calculate the proper time, how to do this. And in general, we have to take integral from such expression. And this is just straightforward our equations of motion. You can put here our general expression for C, but this integration is complicated and the results are quite lengthy, and I don't want to show you this because it would be probably unpleasant. And there, for Schwarzschild, there is a simple way to do this. And because for Schwarzschild, we can always calculate a position of pericenter, or mathematically speaking, for in Schwarzschild, this f function always has at least one real zero, and with this knowledge you can use this and express our C in the simplified way, and put this function into this integration. So basically, what we will now calculate is the proper time calculated from turning point, which the safest way to say is that, okay, it's a pericenter. So proper time from the pericenter to some point. Okay. Okay. This integral looks like this. It's here we have functions of the Weierstrass functions, and these are Weierstrass zeta elliptic function and Weierstrass sigma elliptic function. Okay, believe me, it's quite simple. And yeah, with this we can now construct our way to calculate the integral, because maybe I will wrong this. See. Okay, so imagine that we have a movement from one point to another. This is a C, I think C0, and here. And this is the position of turning point. So apocenter or pericenter. So it will be marked by C1. And this is our length C. Now you can divide this motion into two parts. On the motion from here will be side 1. So motion from C0 to turning point, and the motion from turning point to this endpoint. And with this, if you know how to calculate time between turning point and any point, you can construct this. And it says, okay, so basically the proper time from one point to another point is a sum of proper times from the initial point to pericenter and from pericenter to endpoint. And with this, you have this expression for proper time. And the same way, you can calculate the coordinate time. And thanks to this, our expressions are quite simple. Yeah. Oh. Okay, so let's take a conclusion and say something about this. So basically what I want to show you is that, okay, you have a new description of the movement in the Schwarzschild metric. And the main properties of our description is that it depends only on initial conditions like energy, angular momentum, and the position which you will choose. It don't depend on turning points, which is quite important, and it is expressed just in the Weierstrass elliptic function. And you can be sure that you have only one formula to describe every type of trajectory, and it will always give you a real value. And as I mentioned in the beginning, this was constructed to use this in the different projects simulation, and we think that it will be very helpful, especially this property that you can choose initial condition and don't worry about evolution and anything. So that's it.
Questions? So I have a question. So the blast of gas points are moving along the basis?
Yes. Yeah, like in the
Like gas.
it's like they don't interact with each other.
There is no pressure.
There is a pressure, but you just put a particle with some initial conditions, and it just it's how to say this. I forgot the word, that they don't interact with each other. You don't have this
Interaction.
Zderzenie po prostu. Collisions between them. It's collisionless gas, of gas. So just put the particle and leave it alone.
So this is a test gas.
Not quite.
It's not self-gravitating.
Right now, no. Maybe we will work on this in the future. I hope so, but it will be harder. And yeah, so it's not self-gravitating, but you can use this, for example, in the description of planets. Like you have quite big group of planets or maybe stars. And then you can, okay, so this is our particles which are not interacting with each other. Maybe there are some interactions with the gravity, but they are not significant that, okay, they interact with each other because the main source of gravitational field is from the black hole, probably in the center. So you try to describe this as from the point of the black hole from the center. And
this is a dust of stars.
It could be. It could be. For me, it's a dust, but for example, for Andrzej, it's a very good model for dark matter. For Patrick, I don't know what is this. Probably just mathematical points for him.
Second, maybe not a question, but so I understand that the main point of this of these formulas is that we don't need to know turning points,
Yes.
and turning points are roots of some polynomial. Yeah?
Yes.
So this is what is good for us.
Yes.
We don't have to solve algebraic equations of fourth order. Yeah?
Yes, it's not a problem when you have, of course, one particle, one trajectory, but if you prepare simulation and you have hundreds, it costs a time for you to calculate this.
And from these formulas, it is good that we don't care about the turning points, but from values of your functions, can you guess whether particle is before the turning point or after the turning point? Can you
Yes,
somehow read it from formulas?
yes, basically, okay, so it depends on, you can always, what's wrong with this?
Something is growing or.
Yes, first,
Yeah, it's not exactly.
the simplest way, just take a derivative. But you can also calculate this function. You can express this function in the language of Legendre elliptic integrals, for example, and you can explicitly calculate for which angle there will be the turning point. Then you know, okay, for this angle we have this turning point, and the turning points are in this position. You can, yes. So I think the basics, the way in which you can evaluate this. But the simplest still is like, okay, if you want to do this, just calculate the zeros of this function, especially for Schwarzschild. Because for Schwarzschild, this is a function of this is a polynomial of fourth degree. You can see that you can take one x in front of this expression, and we have general expressions for the for the zeros of the third degree polynomial. Kramer equation, I think they call it. And then you can examine that, okay, are they real or are they complex, and which point is this? Because sometimes you can from this obtain 3 real values. And what it means? It means that, for example, if you write down effective potential, it means that, okay, here, and here, not here, so in 0, and that, okay, if you have particle which comes from infinity, then it will turn back here. But if you have particle which starts something here in this well of potential, then the turning point will be here. So also we need to be specific. What are you interested in?
Thank you. More questions? Online questions? No. So thank you again.
Okay.